Cool. All right. Hi, guys. So welcome to lecture 7. So today we're going to switch gears again. And not completely. We're still going to talk about interactive proofs. But we're going to talk about zero knowledge today. So let me motivate that. So far, so we've been studying interactive proofs, which capture formally the benefits of interaction and randomness insofar as the verification of languages goes. And we've seen, various benefits. For example, we saw that through interaction and randomness, we're able to capture many more languages beyond, classical mathematical proofs. So coin p, p to the share p, and all the way up to p space. We were also, even for languages that are tractable, that we can solve on our own, we saw that interactive proofs can help with delegation. Okay, not all tractable computations, but at least interesting classes. For example, last time we saw bounded depth circuits. Today we learn about an additional benefit, which is zero knowledge. Now, informally, this means that we want to protect the privacy of the prover by designing interactive proofs that do not kind of give away, why a statement is true. Okay. And remember, the prover is, convincing the verifier that some statement is true. So, at minimum, it is solving the computational problem that is associated with it. Deciding whether X is in the language or not, and figuring out that answer may involve kind of coming up with some, important information about, why X really is in L or in the language or not. And zero knowledge is about protecting, this additional information. Now, so graph isomorphism is a wonderful sort of example for many things, not just as a simple interactive proof before we get into arithmetization, not only also as a type of interactive proof for which we can obtain public coins fairly easily, but yet again it will come back, and it's a very nice example to use to illustrate basic properties about zero knowledge. So we'll use that today as the running example. So just to remind you, graph isomorphism is the language where we have two graphs, G0 and G1, and we want to convince that a verifier that they're isomorphic. Okay, but wait a second, this language is anyways an NP, so we do have an interactive proof. It's just the NP proof, right? So the last time we talked about graphs and isomorphism, it was about graph non-isomorphism. Okay, that was some coin p style language for which we didn't have a classical mathematical proof. But actually today we're gonna study graph isomorphism. Okay, that actually is an NP. However, the twist is going to be that now we're going to consider the isomorphism itself that kind of witnesses the fact that G0 and G1 are isomorphic. We're going to consider it as a private input of the prover that is to be protected. Okay, so there is a trivial interactive proof because the language is an NP. The prover sends the isomorphism to the verifier. That works, but it violates kind of this sort of new requirement that we want to kind of protect this private input. Okay? So again, still at high level, how do we design an alternative interactive proof for graph isomorphism that is still complete and sound, right? So the honest prover can convince the verifier that two graphs are isomorphic when indeed they are, and it can't when they're not. But with revealing no information about any isomorphism between G0 and G1. Okay? So that is roughly the goal for today. All of this is informal. The main thing I wanted to put in context is that sort of interactive proofs bring a variety of benefits. Zero knowledge is one of them, and we're discussing that today. Any questions about the motivation here? Now, I should say that we'll not discuss it much in this course, but sort of the property of zero knowledge is very useful in the real world, and to construct efficient zero knowledge proofs, one of the foundations for that is indeed sort of many of the tools that we talk about in this course. All right, so before we even start discussing definitions about zero knowledge, let's just look at some example. So here's an alternative proof for graph isomorphism. I'm just going to write it down because, you know, it kind of comes out a little bit out of a magic hat. But so we have, again, like a prover and a verifier. They have a shared input, which is the instance that we're considering. So the two graphs, G0 and G1. But now notice that I'm making as an explicit input also this isomorphism sigma. Okay, so this is a permutation from G0 to G1 that demonstrates that G0 and G1 are isomorphic, and we want to protect kind of that private input. So here's an alternative way that the prover could convince the verifier that the two graphs are isomorphic. The first thing it's going to do, it's going to sample a random permutation from n to n, and it's just going to pick a random graph in the isomorphism class of G0, which, by the way, is the same, like when G0 is isomorphic to G1, it is the same isomorphism class as G1, right? So this is just a random graph isomorphic to G0 and G1. The verifier then is going to say, okay, well, thank you for sending me a random graph in the allegedly isomorphism class for both. Would you mind telling me an explicit isomorphism from this graph to either G0 or G1? So that's exactly what the prover is expected to do. It says, okay, if B is 0, then, you know, we're supposed to exhibit an isomorphism from H to G0, and otherwise from H to G1, okay? Or rather from G0 to H or in G1 to H, okay? So this seems like a sort of indirect way, somewhat convoluted way of doing interactive proof, but let's first carefully go through completeness and soundness to at least convince ourselves that it is indeed an interactive proof. And then we can talk about whether it is any more sort of private than the prior one of just sending the isomorphism sigma, okay? So let's see. For completeness, we want to say, okay, suppose for a moment that the two graphs are indeed isomorphic. And also suppose that the private input is correct for the prover, so that indeed sigma is an isomorphism, in this case from G1 to G0. Is it indeed the case that the prover can always convince the verifier to accept? Well, look, this is the test that the verifier is doing, right? And this test basically says it's challenging the prover to exhibit an isomorphism from GB to H. But, you know, look, like G0 and G1 are isomorphic, and the prover is just doing whatever he will be tested on, right? Because this is the test of the verifier. Well, because this isomorphism psi is chosen in this way, and sigma is an isomorphism from G1 to G0, when B is 0, then this is just phi of G0, which is true, because that is how H was chosen. Otherwise, when B is 1, well, sigma applied to G1 is G0, and then we just have again phi of G0, okay? This is just notation for saying that if indeed the two graphs are isomorphic and the verifier is interested to connect H to G0 or G1, then the prover can always do that. And this is the particular way in which he's going to do it. Okay? All right, so nothing too surprising there. Soundness is also actually even simpler to think about because, look, if the two graphs are not isomorphic, then in this first message, the prover puts his foot down and says, here's a graph H, that he's allegedly claiming isomorphic to both. But if they're not isomorphic, then H will be isomorphic to at most one of them, right? So because it is isomorphic to at most one of G0 or G1, then any malicious prover will get caught with probability at least a half, right? Because with probability at least a half, B will be something for which H is just not isomorphic to it. And so there's nothing the prover can do here to pass the test. Okay? So are we all on the same page that this alternative protocol is an actual interactive proof for graph isomorphism? I mean, it's just different than just sending sigma, right? Sigma is participating, but just something else is happening in interaction. Are we on the same page about that? Okay. Now, to argue completeness and to argue soundness, we had definitions to go with them, right? To argue completeness, we wanted to say that the probability the verifier accepts is very high, or 1, when G0 and G1 is in GI. In soundness, we also had a definition. It says we want to show that the verifier rejects with high probability when they're not isomorphic. If we want to argue that this protocol has some sort of zero knowledge property or some privacy property, we need to first argue what the hell zero knowledge means. Okay? So typically it is useful to think first of a relaxation of zero knowledge, which is known as honest verifier zero knowledge. Okay? So we're going to first explain this notion. I'm going to first write down the definition, parse it. I think it's just simpler to, like, in my opinion, it's just simpler to first see the definition, and we're going to try to interpret why that captures what we would like. So here's the definition. It's very short. It says, if you give me an interactive proof, here's the prover and the verifier for some language, we're going to say that it is, in this case, honest verifier zero knowledge if a certain condition holds. Now, this condition will talk about, basically what the verifier learns in a certain context. So we're going to be talking about a view. I'll define the view in a moment. But the main point is that the condition says that there is some so-called simulator S, okay, that is efficient. So it runs in probabilistic polynomial time. So this is an efficient randomized algorithm, such that anytime you pass it a true statement, X in L, then this simulator is capable of basically reproducing the view of the verifier that it would have had in an interaction with the actual prover. Okay? Now let's just think for a moment about what is this view. Well, it's whatever the verifier has seen. What does the verifier see? Its own randomness, let's call it R, the input, of course, X, and all the prover messages. The verifier messages, I don't need to write them, they're just implied by everything else here, right? So the view, it's not just some, I don't know, like philosophical thing or like ill-defined, it is exactly this tuple, okay? The view is a random variable that consists of the uniformly random sampled random tape for the verifier, the specific fixed input, and whatever implied distribution is about A1 through AK, okay? Now this implied distribution, of course, is correlated with R because, some of these answers may be answers to messages from the verifier, but the prover itself might be using randomness, okay? Notice in the prior slide, in the protocol that we wrote down, the prover was using randomness, and I'll talk a little bit more about randomness later. But so this is basically a random variable, and we want to say that this random variable can be recreated by an efficient procedure that doesn't interact with the prover. Okay, so the interpretation for this property says that the honest verifier could have simulated the whole interaction by himself without talking to the honest prover. Okay, because again, the prover is doing something magical here. It is convincing the verifier that X is in L for some hard language L. Possibly we're worrying, maybe the verifier, by being convinced and seeing the prover messages, he will learn some non-trivial information about X. But that can't be really, right? Because given that X is in L, the simulator can just look at X and, I don't know, in quadratic time, figure out how to sample this whole view, right? So kind of from a statistical perspective, this view doesn't contain any information that cannot be produced efficiently just from the input alone. Okay? Are people comfortable with this definition? For those of you that have some background in cryptography, it should be pretty simple because this is something known as the simulator paradigm, and it is used to define a million things in cryptography. Basically, almost everything in cryptography can be phrased as some simulation game. Any privacy goal in cryptography can be sort of phrased as some simulation game, and its roots are, in zero knowledge. It's a very powerful sort of a way of phrasing, rather than saying that defining kind of what is knowledge and not knowledge, you just say, like this is the thing that, the verifier knows, X, we are considering the good case, let the simulator do everything, and then whatever this thing is, as complicated as it is, if I can create it just from X and randomness, it can't contain anything too interesting. Questions about this? Okay. Now notice that honest-verifier zero-knowledge is neither a property of the prover or the verifier, but is a joint property of the prover and the verifier. Why? Because, look, we said that we are going to specifically look at the view of the honest verifier when it interacts with the honest prover. Okay? So this is in contrast to, for example, a soundness property, which is a property of the verifier, right? In a soundness, we just quantify over all provers, and we argue that the verifier on its own is able to kind of protect himself, right? Here is saying that, provided that the honest prover behaves according to the protocol, and also the verifier behaves according to the protocol, then the simulator will succeed in sampling this view. That's why this is known as honest-verifier zero-knowledge. Notice, of course, that whenever we talk about zero-knowledge, we are always talking about an honest prover, because it's pretty hard to safeguard the privacy of provers who do not want to be protected. A dishonest prover could just say, screw the protocol, I'll send over my private input. What are you going to do? There's nothing you can do about that, right? So we're always talking about honest provers. In this case, we're also talking about an honest verifier, right? But I'm lingering here for a bit because this definition is, it's very short, but it packs something non-trivial. It's quite expressive in sort of what it demands. Any questions about this? Okay, so in that case, now that we have down a definition, we saw an example. Let's see if that example meets this definition. Okay, so let's prove that this protocol from the previous slide, which we have already established is a interactive proof for graph isomorphism, indeed satisfies the property of honest verifier zero-knowledge. Again, zero-knowledge is not an opinion. It is a definition needs to be fulfilled. So how are we going to fulfill this definition? Well, first, we have to fix two graphs that must be isomorphic because we're only considering instances in the language. Okay? Again, we're looking at the honest prover. The honest prover is only doing something when X is in the language. Otherwise, the protocol will not make sense. And before you construct the simulator, you should at least clarify to yourself what is the view in this particular case. Well, in this case, let's see. The verifier sees the graphs. Well, okay, we can agree on that. And remember, the graphs are isomorphic. Its only randomness is just this one bit B. So let's just put the whole transcript down, and that includes everything. First message, only randomness of the verifier, and the second message of the prover. This is everything in the verifier's view. There's nothing else, okay? Input, first prover message, randomness of the verifier, second prover message. Okay, but what we're actually interested in is what is the distribution of this thing. Now, G0 and G1 are just fixed, okay? So that there's no randomness there. What is H? Well, H is just a random graph in the isomorphism class of G0, okay? B is a random bit, and psi is a random permutation conditioned on being isomorphic to GB, okay? Not isomorphic, so it's random permutation between H and GB specifically. Okay, well, that's the distribution. Now, the definition asks us, please exhibit an efficient randomized algorithm, namely a probabilistic polynomial time algorithm, that will produce this very same random variable without doing anything inefficient, basically, right? So you just give me the graphs, and I need to produce all this stuff, right? Now, notice that here the prover when we were implementing this procedure, he had sigma. This was an isomorphism that was given to us. And because the prover had this, he could compute easily this psi, right? Now, imagine if I'm the simulator and I say, okay, well, let me just do this step, that I can do it, and I just write down H, I sample B, but then how am I going to do this step? Like, I don't have the sigma. Finding sigma might be inefficient, right? So the simulator has to do something a little bit differently. And here we'll use the fact that the simulator doesn't have to proceed in a doesn't have a notion of time. Like, it doesn't have to talk to an actual verifier. It just needs to write down a view that is distributed like the view of the verifier. So it can sample these objects in a different order. And by sampling the objects in a different order, it will actually be able to produce them. So this is what it's going to do. It's going to first sample B, a random bit. Then psi is going to be a random permutation on its own. From B and psi, you compute H, and you complete the transcript down here. Okay? And let's see, syntactically, this is correct, right? It is a quadruple, where this is G0 and G1. This is some graph, some bit, and some permutation. So far, so good. But what they're interested in is, is this distributed correctly? Well, let's see. H is supposed to be, let's start from psi. Now from H. H is supposed to be some random graph isomorphic to G0 or G1, right? But look, G0 is isomorphic to G1. It doesn't matter if we start from G0 or G1. Here we started from G0 and we moved to a random graph. Here, whether we start to G0 or G1, it doesn't matter. They're isomorphic. They're in the same equivalence class. So H, as computed here and as computed here, they're distributed identically. Okay? Then B, well, that's a random bit here, and that's also a random bit here. And psi here is random subject to this condition. But look, H was created to have this condition, so we're good. So the two random variables here and here are like literally the same random variable. Any questions about this?
Just to clarify the intuition, in this case, whenever this pair is honest verifier, zero knowledge, then the prover basically doesn't do any useful work because the verifier could do it all themselves, right?
The question was, whenever we have honest verifier zero knowledge, is it the case that the prover is not doing any useful work because the verifier, can sort of do it by itself? It is doing at least something. It is convincing the verifier, right? But the definition already takes care of that. So let's go back to the definition. We are only considering X is in L. So there is this one bit of information, is X in L or is X not in L, right? And the prover is convincing the verifier that X is in L. So we're already modding out basically by this bit of information. And once we mod it out by this, we say, well, everything else, it is something the verifier could have indeed generated on its own, right? So, I mean, the interactive proof is useful for something, right? Otherwise, why talk to the prover? There is a reason to talk to the prover, is to be convinced. But you want to basically upper bound and say, that is all you're going to get from this interaction is to be convinced. So this is kind of modding out by that bit of information. And more generally, in cryptography, when you use the simulator paradigm to kind of try to formalize some privacy condition, you typically try to clarify to yourself, in some protocol, what do I expect the other party to know anyways, or some necessary piece of information that must be leaked, right? Just by functionality, that is kind of the correctness of the system. You give all this stuff to the simulator, and you want to argue that outside of this kind of necessary leakage, everything else is fine. Here, in the case of proof system, the necessary leakage is the functionality of the proof system that you convince the verifier. You mod out by that, and everything else is taken care of. Now, I think So there's something important to kind of, I think, maybe think about offline. Some people, when they see this first simulator, they think it's like cheating, that it samples things out of order. But remember that kind of it's literally the same random variable, right? The only reason why we have orders in a certain way is just for soundness. At the same time, you can't expect the simulator to like literally do the same thing as the prover. Otherwise, this could be used to break soundness, okay? So this is actually something that can be formalized, that if you're not using, some extra property here, you can't expect to kind of also be sound. So the simulator always needs some edge. So that's fine from a formal perspective, but from a meaningfulness perspective, it's important to realize that kind of there was nothing about the order of the messages that was about information content. Like who cares about the order of the messages for information content? What we're interested in to quantify information content here, like to argue whether there is like non-trivial information or not, is kind of, can you create this random variable by yourself, right? Because in the end, when the verifier goes away, like that's what it has in its pocket, or that's what it remembers. It is this random variable, right? It doesn't matter the dynamic process that created it, right? So the information it walks away with is a sample from this distribution. And so that is exactly what the simulator says, that a sample from this distribution was cheap to generate. So you're walking away with nothing interesting. The interaction was just for soundness, okay? So that's important to kind of internalize. So that's like, there is something like sort of slippery about not the syntax of this definition, just like the meaning of it. But it's pretty robust. Okay, that is honest-verifier zero knowledge. Any questions about this before we move to, I guess, malicious-verifier zero knowledge?
Professor, could you say briefly again, like why the interaction is just for soundness?
Sure. So the intuition is that after the interaction is done, you're asking, did the verifier learn something, right? So now imagine the verifier is done interacting, he goes home and sits at his desk and inspects what he learned during the interaction. What does he have? This, a sample from this distribution, right? That's all he has, right? So, and we're saying that a sample from this distribution is worth nothing, okay? Beyond just being convinced. So that is, I think, the mental picture to keep in mind, right? Sort of after the interaction is over, like what did the verifier learn? Well, a sample from this distribution. And we're saying, this sample is easy to sample by yourself, right? So you could have, if any experiment you can do or like learning you can do about this, you could have instead done by saying, I'll run the simulator and just go home and study this instead. And it would be literally the same thing. So there's some questions here, let me answer them. This assumes that the randomness of the verifier is from a distribution that is easy to sample. Yeah, all probabilistic algorithms by definition have a random tape that is a random tape. That would not be like a probabilistic polynomial time algorithm if it had sort of help from some hard to sample distribution. So that would not be that. And remember that we have this is an interactive proof. So we have already assumed that the verifier is just a normal probabilistic polynomial time machine. So it cannot be designed to have, it can't have sort of help from funny distributions. The issue about where does the randomness come from comes up when you consider inefficient verifiers. Sometimes you consider zero knowledge against inefficient verifiers, and you need to do something a little bit different for the randomness, because it's not just it could be from a different distribution, it could just be enormous, the randomness itself. So there's a question about, do we have to assume that H was actually picked randomly and that B is picked randomly too, meaning uniformly at random? Here, we are definitely assuming that H was picked randomly because we are trying to protect the honest prover. And so, like, the honest prover will follow the instructions because he's honest. And because we're looking at honest verifier zero knowledge, we're also assuming that the verifier is honest and B is random. We're about to deal with the case if B is not random. That would be malicious verifier zero knowledge. Good questions. Okay, I don't think I missed other questions. Okay. Any other questions before we move to malicious verifier? Okay. So now more generally, it seems more meaningful to consider zero knowledge also against malicious verifiers, because imagine a protocol that is merely honest verifier zero knowledge, but not malicious verifier zero knowledge. Well, that seems pretty strong incentive to deviate from the protocol, because you might learn some useful information. So sometimes you also want to consider the case where even if the verifier deviates from the prescribed protocol, then they learn nothing. So, okay, how do we say that? Well, now we say an interactive proof for a language is malicious verifier zero knowledge. And here I put malicious verifier in parentheses because typically if it is left implicit, like you make explicit only when you're saying honest verifier, but when you don't talk about it, it usually means that you're already talking about malicious verifier. Through this lecture, I will always make it explicit, but just be mindful that in the literature, when you don't see it, it is malicious verifier. If there exists a polynomial time simulator such that where now, just like before, we were considering every x in L, but now we need to ask the simulator to say, look, I have some malicious verifier here, some efficient malicious verifier. Why efficient? Because if it was inefficient, then he can just go and learn the things he wants, right? He doesn't need to go and ask for the prover's help. That's not really a full answer, but that's roughly the reason why we are restricting that here. We really want to say, what would they learn beyond polynomial time? So just fix some arbitrary algorithm that runs in probabilistic polynomial time. Now, the simulator also needs to know about it, right? Before, the simulator would get just the instance as input because it knows what is the honest verifier. But now, like, the simulator will be called upon to simulate the view of a malicious verifier. So you better tell him which malicious verifier you're currently considering. Now, one important relaxation that happens in this definition is that we're only asking the simulator to be polynomial time in expectation. This is mostly, we're forced to do it because it's just very hard to construct simulators against malicious verifiers that run in strict polynomial time. It happens primarily not for interactive proofs, for other types of proofs. So this is just like I don't know, like we just swallow this relaxation, but it's still meaningful, right? So we're saying that this time the view, instead of being sampled by an algorithm that at every input runs in strict polynomial time, is just in expectation, right? So remember, a polynomial time algorithm, the running time of a probabilistic algorithm is itself a random variable. And we're saying that the expectation of that running time is polynomial. Okay, that's what we're saying here. So that's just a relaxation, and we'll see immediately, well, we're going to be using it right away. And there are some results that talk about how strict polynomial time simulators are not really very powerful. And here the intuition is that even verifiers that deviate from the prescribed protocol cannot learn any information besides the bit x's in L. Okay. Now notice that because now we are considering malicious verifiers, now zero knowledge becomes a property of the honest prover alone. The honest prover is just safeguarded, period. It doesn't matter what the verifier does. Okay. So like this is a pretty strong property. Okay. Analogous to how soundness is a pretty strong property. Soundness says that the honest verifier is safeguarded against all malicious provers no matter what. Right. Here we're saying that the honest prover is safeguarded against all malicious verifiers, efficient ones, no matter what. Okay, and here, we're just writing down each of the properties we've seen. Are they about prover and verifier, or verifier alone, or prover and verifier again? Right. In this case, it is honest prover alone. Right, and then I already talked about this expectation relaxation. Are there questions about this strengthening? I think once you feel comfortable with honest verifier zero knowledge, I think the step from honest to malicious is pretty, I mean, it makes sense. Yeah. Okay. So we have a definition. Let's try to work with it. And we will go back to the same protocol as before and show that, in fact, it is also malicious verifier zero knowledge. This should not be taken for granted. Like, there are plenty of protocols that are just honest verifier zero knowledge, and they're not malicious verifier zero knowledge. Now, this particular one that we've seen and analyzed already for honest verifier zero knowledge happens to satisfy the stronger notion. How convenient, right? So let's do that. Again, like before, zero knowledge is not an opinion, it is a mathematical property. So to fulfill it, we just need to go through the definition and show that it is fulfilled. The definition asks us not only to fix two graphs that are isomorphic, but also fix a malicious verifier. Okay? And like before, we should at least clarify to ourselves what is the distribution of the view of a malicious verifier in this protocol. Well, it is a tuple that looks like this. Now I am denoting the bit B, which is the one message from the verifier, to be with a, actually now I notice that I should fix the slide and also add the randomness here, because maybe, yeah, do I need the randomness? Maybe not, actually, never mind. I think I can assume without those generality the malicious verifier doesn't have more randomness because it doesn't really matter. What was I saying? Right, so the bit B here, I denoted with a tilde because, it may not be random, right? So what is this thing? It is, like before, H was sent by the honest prover, so it's just a random graph isomorphic to G0, which, because G0 and G1 are isomorphic, is just a random graph isomorphic to both. B tilde is, whatever V tilde outputs given H, right? It's whatever it says. The honest protocol says random, but, this verifier may just look at the graph H and make some complicated computations and output some biased bit according to some probability that, that the malicious verifier decided was appropriate to attack this protocol, right? And again, based on that, psi is random such that H of that, and actually here I'm missing a tilde, so let me add it here. So that's just analyzing the view of the malicious verifier. Now, like before, we need to exhibit a simulator that now we are allowed to run in expected polynomial time, and it has to be able to produce this random variable. Okay? Now, obviously, we're going to have to use somewhere the verifier itself, because we can't know a priori what the verifier is going to do, which distribution it is going to use. So here are the steps. So let's go through them. It's almost the same, really. It's saying, okay, let's sample a random bit B, ignoring the verifier first, then sample psi like before, compute H based on psi and GB, and then we say, well, yeah, I haven't really asked the verifier what he would have done anyways, so let me ask him, and he's gonna tell me some bit B, and if I was wrong in guessing, I'll just go back and try again. Okay? And this seems like it sounds fishy, right? So first and foremost, let me ask you, why doesn't the verifier, imagine that the verifier, malicious verifier, is trying to thwart this simulator, right? One way to thwart this simulator would be to make the simulator never halt. How would you make the simulator never halt? You make sure that when you receive H, which was derived from B, when you receive H, you output always B tilde that is different from B. Why can't the malicious verifier do that?
Because then you would be able to figure out which
which graph H came from?
Yeah, but why can't specifically, why can't the verifier figure out which graph it came from?
Well, you could also just sample the guess bit later, so it's sampled after the verifier sends it, and then it's independent.
The question was, well, the suggestion was, maybe why don't I sample B later? Well, that's going to put me in trouble, right? Because kind of the only way that I know how to provide psi as a last message is if I compute H from psi and B. But in order to get B tilde, I need to have H already. So I really need this order. But there's a concrete reason for why V tilde cannot know any information about B. Why can't V tilde not know any information about B? Okay, so there's a suggestion in the chat because H is independent of B. Correct. So why is H independent of B? Because, look, H is just a random graph isomorphic to GB, but wait a second, G0 and G1 are isomorphic. Look, I have to use this somewhere, right? That they're isomorphic. And here it comes exactly here, right? So H sampled in this way carries no information at all about B. So there's just no way that V tilde can do that, okay? So that's kind of what I'm saying here. Since G0 is isomorphic to G1, H is independent of B, and so H is also, and so B is independent of B tilde, okay? Because of that, the probability that B tilde equals B is a half, no matter how malicious or determined V tilde is, right? This means that the expected number of rewinds of my simulator is 2. So that this simulator runs in polynomial time, right? Sort of each run is in polynomial time, and if I have an expected number of rewinds to be 2, then I'm just paying twice this cost. So that runs in expected polynomial time. Now, of course, there is some small probability that it will run long, right? A long time. But whatever. Right now, I'm just asking expected polynomial time, so that's okay. All right, but it doesn't mean the simulator works. It just means the simulator is efficient. We also need to argue that the bit that I eventually output is distributed correctly. Can anybody say why that is the case? There's a buzzword that I'm looking for.
Well, isn't it the one that the verifier would have output while we ran the interactive proof in the first place?
Yeah, but there's potentially some bias here, right? So there isn't bias, but we need to argue that, right? So I am potentially, suppose that I happen to go through 7 iterations of this thing, right? And eventually I output B tilde, right? So in principle, outputting on the 7th time rather than the first time biases the distribution of B tilde, right? So, right, so in general, that may happen, but it doesn't, okay? Because they're independent. So what we're doing here is just rejection sampling. We want to say that the probability that B tilde equals 0, given that I do halt, right, is the same as B tilde equals 0 on its own without messing with any conditioning, right? And if you just kind of expand this out, because B and B tilde are independent, I can sort of pull out the probability that they equal, okay? And sort of they cancel out, and overall I have that when I do output something, it is with the correct bias, okay? So again, all of this is just the fact that the simulator runs in expected polynomial time and that I am doing the right thing. They're both kind of direct implications of the fact that B and B tilde are independent, okay? And why are they independent? Because I'm in the good case. I know the graphs are isomorphic, and so H carries absolutely no information about B, just statistically. Okay? And that's it. Now you have a simulator for this case as well. And this is representative of how you construct many zero-knowledge proofs. You're going to be using some clever rewinding techniques. And in this case, it's just like, rather elementary rewinding technique. There's a question about, is this kind of like the memoryless property? Yeah, I mean, in every run, I sample a new B, right? So it doesn't matter which B's I sampled in past invocations, and in every run, I have an independent probability that B equals B tilde, right? So I'm just ignoring what happened before, and so kind of every run is on its own, because I'm kind of sampling all the randomness afresh each time. Okay? All right. An interesting point here that turns out to be very important in the theory of zero-knowledge proofs, I'll just kind of mention it here, is that almost every, but not every, zero-knowledge proof that you're going to see, the verifier, which is given to the simulator, the simulator is not going to really use the verifier. It's just going to press play, stop, rewind. It's going to have like an extremely limited use of the verifier. It's not going to like look inside and see, kind of how it's trying to reason. This is just not that. It's making a so-called black box use of the verifier. It turns out that, on the cryptographic side of things that, we don't really study much in this course, how exactly the simulator sort of touches the verifier, leads to like different types of zero-knowledge proofs insofar at round complexity, public versus private coins, and sort of so many important considerations like composability, many important considerations like revolve around how the simulator uses a malicious verifier, and quite amazingly, there are examples of zero-knowledge proofs that make a non-black box use of the verifier, which should sound extremely surprising because V tilde is a generic algorithm. A generic algorithm may have been written in a language that hasn't been invented yet. It just computes, right? So it should somehow be kind of surprising that such things are possible, yet they are. Okay, so that's about malicious verifiers knowledge for graph isomorphism. And obviously the world is not just graph isomorphism, kind of what happens more generally. Now, in the particular case of interactive proofs, it's mostly bad news, actually. So specifically, we can define complexity classes that correspond to these two notions. Let's define them let's call them HVZK IP to be all languages that have interactive proofs with honest verifier zero knowledge, and MV or just no MV, just ZK IP to be all languages that have interactive proofs with malicious verifier zero knowledge. And, because we are, adding restrictions each time, it is clear that, these inclusions hold, right? We're just adding restrictions each time, so this cannot go up the set of languages. It can only at the best, become smaller. And also, it is not completely empty as a complexity class because all tractable languages are by definition zero knowledge because the simulator has nothing to do. It can just sort of, the verifier doesn't have to talk to the prover. The simulator doesn't have to do anything. So the end. So it's not completely trivial. It's just trivial in a different way that, there was no interactive proof happening. But we have established that there is something interesting because GI is not known to be in BPP, and yet we have exhibited that there is a malicious verifier zero-knowledge interactive proof. So kind of, you can ask, what other languages have zero-knowledge interactive proofs? So we do have like a pretty good understanding of the answer to this question. Here it is. This is something I will not be proving. It's a pretty sort of technical result. But let me parse it for you so we understand the consequences. So here we're saying, let's study the more relaxed notion of honest verifier zero knowledge, so the bigger of the two classes. and say bad news about it, about the bigger of the two classes. Why is this bad news? So this is basically saying AM intersect co-AM. So we've encountered these classes before. AM is public coin interactive proofs, and here it specifically says 1 round actually. When you don't specify number of rounds, it means 1. So this is saying every language that has any honest verifier zero knowledge interactive proof has both a 1 round public coin interactive proof, and its complement also has one. Now, okay, in principle, okay, who cares? Like, I like 1 round public coin interactive proofs. What's the problem with that? Well, if you're in this intersection, then a NP can't be inside it, for example, okay? So, like a very pleasant target, like NP, for example, it would be nice to have a zero knowledge interactive proof for SAT, where you're protecting some satisfying assignment for a formula. It is, we don't expect NP to be contained in this intersection. That would make very bad things happen in the complexity hierarchy. So yeah, like that's pretty sad. So basically, what kind of problems do we have in this class? Well, we have GI, we have quadratic residuosity, some simple lattice problems, not much else. I mean, there's some pretty technical, not super useful problems. And this limitation holds even if we relax the requirement of the simulator to require that whatever the simulator outputs and the honest view are merely statistically close rather than equal. So statistically close, I mean in total variation distance. You could just ask, just simulator, I just want you to be, mostly from the same distribution, just not too far, please, rather than literally the same distribution. That's a relaxation. That's called statistical rather than perfect zero knowledge. And you can consider these classes, and even if you relax them, like this thing continues to hold. So that's pretty annoying. Yet, I'm sure you've heard, we have zero knowledge proofs growing on trees, and you can find them in the woods after it rains, and so where are they coming from, right? Well, that's because we have other ways to overcome these limitations. We will not be talking too much about these in this course, but I want to at least kind of compare and contrast. One option is to relax the requirement on the simulator even further and say that, look, I actually don't care anymore that these two distributions are close. I just want it to be the case that they are hard to distinguish. There's something known as computational indistinguishability. Again, if you have taken a cryptography course, a computational indistinguishability is taught, I don't know, in lecture 1 or lecture 2. It is like a foundational notion in cryptography. It just says that no efficient algorithm can tell the difference whether a sample comes from here or from here. And this further relaxes the meaningfulness of zero knowledge, but it's still pretty meaningful. And when you do that, you can define a corresponding classes, honest-verifier computational zero knowledge and malicious-verifier computational zero knowledge. And here there is like a foundational result that says that if something very minimal happens, one-way functions exist. Again, I haven't defined them, but let me tell you, in cryptography, it's like a rather minimal assumption, so it's like kind of not a worry. Then under very plausible assumptions, every language that has an interactive proof actually can be turned into an interactive proof that is malicious-verifier computational zero knowledge. So this is still an interactive proof, so soundness holds against unbounded provers. It's just the honest prover, he's only protected against he's only protected against efficient verifiers in the sense that no efficient distinguisher can tell apart the output of the simulator and the real execution between the honest prover and an efficient malicious verifier. Okay? So it's a very strong result. It's in fact surprising that with one-way functions you can go so far. It's also a beautiful result. So this is one way in which actually there is like many interactive proofs, like, in particular, because we know that IP equals P space, doesn't just give you interactive proofs for NP, it gives you interactive proofs for P space as well. So zero knowledge proof, not just for NP, but zero knowledge proofs for P space as well. So that's like all the languages you ever wanted. So, and thanks to this, there was like a long line of work spanning, 30, 40 years exploring sort of many constructions of zero knowledge proofs in the cryptographic setting. Another option is to say, it's an interactive proof fault. Let's just think of like different models of probabilistic proofs. Actually, we'll do that next lecture, not about zero knowledge, but we'll start talking about something other than probabilistic proofs. We'll start talking about probabilistically checkable proofs, and there are just other types of probabilistic proofs that are useful in like different contexts. And each of them behaves quite differently with respect to zero knowledge. It's just interactive proofs are the ones that are most restricted. There's some intuition for why that is the case, but somehow like they're like the least lucky ones as far as zero knowledge goes. And here, maybe I'll just highlight one model that we will, that is very, very close to interactive proofs, and is about multi-prover interactive proofs. So imagine the verifier, rather than talking to one prover, is talking to multiple provers. Why would you do that? Well, you know, why would you even talk about interactive proof? Because it has applications, right? So multi-prover interactive proofs also has applications, both to cryptography and complexity theory. And now the provers cannot talk to one another, but otherwise it is just like an interactive proof. And in this model, actually, without any cryptography, you can show that every language that has a multi-prover interactive proof can be made perfect zero knowledge. Another beautiful result, very powerful. And it's interesting to contrast these things because here it's basically saying, all right, if you want to make everything provable in your model be zero knowledge, you need just a minimal cryptographic assumption. And here it's saying if you want to take everything provable within your proof model, zero knowledge, well, you don't have to do anything because this model is kind of nicer. But we've done a trade-off, like we kind of exchange cryptography by some physical assumptions, some implicit physical assumption. Like, why are there two provers? Because they can talk to one another. But why can't they talk to one another? Because there's a big wall between them, or they're in Faraday cages, or whatever, right? So there is something that kind of was done to kind of enable this, and that is this kind of separation of the prover strategies into like kind of so that they cannot talk during the interaction. So this is just like a bird's eye view of the, I would say, the two main ways to kind of create zero knowledge beyond the extremely restricted setting of just everything information theoretic and only about interactive proofs, which is quite limited in the previous slide. Whereas here they give you like a sort of more powerful results. Now both of these are, you know, well beyond the scope of this class, but I did want to mention them just so that you don't leave this lecture thinking, oh, zero knowledge proofs suck because like they only exist inside AM intersect co-AM. Now I've said a lot in this slide, and also about things I didn't define, like this one and this one. And typically we do define almost everything. So there's a question that says, does option 2 give perfect ZK or computational? Perfect ZK, I put a P here, specifically about perfect ZK. So in this option 2, everything is statistical. You get statistical soundness and, in fact, perfect zero knowledge. It's as strong as you, and even with two provers, you don't even need like, I don't know, 15 provers. Two provers are enough. So it's a very, very strong statement. More questions about this slide. This is more, I guess, a context slide. Yeah, and you can build like an entire course just around like, you know, talking only about zero knowledge. There's a lot of things happening. All right, so now what I would like to do is just spend maybe a couple of slides, just in the remaining 15 minutes, giving absolute minimal intuition about why in the particular case of interactive proofs, just suddenly the moment you have a simulator, it means that your language cannot be too hard. Like the existence of a simulator kind of limits the expressivity of the interactive proof. And it's really like, I don't know, like perverse intuition. It's very strange. Like, so let's kind of go through it. So here's like some, one of the lemmas that go behind the theorem I mentioned earlier about the limitations. It says that if your language has an honest verifier zero knowledge interactive proof with, say, k rounds, then its complement has has just a normal interactive proof with roughly k rounds. And kind of how you get started in this lemma, which we're not gonna see in full. We're gonna see just an example. But how you get started in this lemma is like very curious. It says, okay, well, okay, if the language is in this class, give me the interactive proof that satisfies this property. And because it satisfies this property, there is a simulator. Okay, so far so good. We know from the guarantee of the simulator that whenever the simulator is run on X that is in L, this property holds, like it simulates this view. In fact, here we're just looking at honest-verifier, so even limiting just honest-verifier, not even malicious. And you can just ask, I have a simulator, it's a machine, what would it do if X is not in L, right? I can just like plug in X not in L and see what happens, right? After all, if I'm gonna prove some limitation on zero-knowledge proofs, I'm gonna have to use the simulator somehow, right? So now I'm gonna try to start abusing the simulator and see what it would do on an input it wasn't designed to do anything for. And okay, well, it will do something, right? So it might just start outputting garbage, like it might explode along the way. It might output like something that is nonsensical. That is an option, right? It could be. He could output some view, just a rejecting one. It's just saying, something that is not completely nonsensical. Remember, the simulator was supposed to output an accepting view, right? So here I'm just saying, suppose it outputs, I don't know, banana. But in option 2, it says it outputs a view, it's the view of verifier that rejected. A third option is that it could output a view that is accepting, but really 1 and 2 are not that interesting, right? Because if that's what the simulator was doing, then the language could not have been hard, right? Because suppose the simulator only ever does either 1 or 2, I could just decide the language myself without the help of the prover. I just run the simulator and I see if it outputs an accepting view, then it must be an X is in L. And if it does either 1 or 2, I can figure it out myself and I just say that X is not an L. So this language cannot be hard. It must be in BPP because the simulator basically decides it. So these options, while syntactically possible, they're just not what is going to happen for an interesting language. For an interesting language, we're going to be in this third option. The simulator is going to fail in some way that is hard to tell by myself. Okay? So it will always be in 3. Now, okay, so it outputs like some accepting view, but if it is indeed the case, it cannot be close in statistical distance to this one. Because, look, we are saying that we're in option 3, the simulator outputs an accepting view, but this view, when X is in L, by soundness, is a rejecting view. Okay? So they must be far apart from each other. So now we have this interesting gap. When X is in L, S outputs something literally from this distribution of accepting transcripts. When X is not in L, the simulator outputs an accepting transcript, but I know it must be far from this one because this one is made up primarily of rejecting transcripts. Okay? So now I have this interesting gap, okay? And yeah, this is like pretty technical, but intuitively, like we can reuse some of the knowledge that from the public coin lecture, this set lower bound protocols. You can use a combination of set lower bound protocols and set upper bound protocols from lecture, whatever it was, 5 or 4, I forget. And basically you can design a new interactive proof for the complement of L by basically arguing about the statistical distance, okay? And it is not something that you can do on your own, but the prover can help you to do. And this is intuitively how you kind of learn something about the complement of L. Now, this feels vague. I'll kind of make it concrete like right now for just a very simple example. What I find super interesting about this is that just trying to abuse the simulator to do something interesting on an input it wasn't designed for. I think that's like really just the mere fact it exists and it causes something interesting. This is kind of it gets in the way of the expressivity of the language. And intuitively it is because it reduces to some question about figuring out the statistical distance between two distributions, and that's like a counting problem that you can deal with like set lower bound protocols in basically, that is not too hard. Now, let's come back for the nth time to graph isomorphism, and we'll see something like pretty interesting. So consider the zero-knowledge interactive proof for graph isomorphism. Here it is. That's the one we studied today. And here is its honest-verifier simulator, because remember, we're just talking about the honest-verifier for right now. All right, so we have already learned that if the two graphs are isomorphic, this simulator right here does the right thing. It outputs a sample from this distribution. We analyzed that earlier. But what would happen if we run this very same simulator on two graphs that are not isomorphic? Look, this algorithm will terminate. Okay, it really will terminate. In fact, it will output an accepting view. It really does, right? It outputs an accepting view. Just it has a funny distribution, right? It's not anymore the case that H is random, from in the isomorphism class of G0 and G1, because they're not isomorphic. So it will either be isomorphic to G0 or G1. And in the prior slide, I argued that because of this thing, it tells us something about the complement of L. But wait a second, like we had an interactive proof for G and I. It was this one. And if you look, the first lines of this proof are actually the code for the simulator, which is like really weird. Like these two proofs were designed independently before this connection was made, that being zero knowledge tells you something about the complement. This proof was designed as a zero knowledge interactive proof. This was designed as a non-zero knowledge interactive proof for a problem outside of NP. Not known to be NP, right? So G and I. And like you can see here the simulator, and you're basically challenging the prover to prove to you that the distribution of H looks funny, very different than if the two graphs had been isomorphic. So this is an interactive proof for graph non-isomorphism. Okay, and you can really see the simulator here. Now in the general theorem, for that kind of that I didn't prove from a prior slide, the new verifier indeed runs the simulator and then kind of engages with the prover to asking the prover to prove that the simulator outputs something that was kind of off from the correct distribution. And here we're doing that, right? Because the prover is able to figure out B tilde, this is indeed because H is distributed in a funny way. Why is it distributed in a funny way? Because G0 and G1 are not isomorphic. Okay? So kind of, you can think about this as basically this exists because we have a zero knowledge proof for graph isomorphism. So this is, I don't know, it's like a very strange and sort of unexpected connection.